Hi, I'm Rob Cook, and I work in operations under LX03. I've been using a lot of my time to work on my Element Operation Manager training. There's a lot of reading and a lot of documents to go over, so being at home helps to have a lot of downtime to be able to read things and catch up on my certification. I've been working hard to be able to have things ready to go ahead of booster stacking so that I can be on the floor and learning how operations work firsthand and hopefully running them. I'm really excited to be able to get flight hardware here and be able to see those booster segments arrive next month. It's been a really exciting process of seeing everything arrive, and we're really close to being able to launch, so I'm excited to be able to have everything come into place and hopefully be a part of the actual assembly of the SLS. For my day, I usually spend it doing modeling support. I've been helping the landing recovery team with simplifying the crew module for the Orion spacecraft. That's been a really frustrating but fun project. It's a lot of problem solving to be able to fix the model and make it run in a smaller package without having to load this gigantic computer model that most people's computer can't load. It can be really challenging to be able to load it in pieces and then reassemble it later, but I like that type of challenge, so it's right up my alley. I've also been supporting some of the mock-ups around the center. One of the main mock-ups that I had a part in is the ICPS equipment shelf mock-up. We were using it to practice the installation of avionics into the upper stage of the SLS. The mock-up gives the technicians a good place to be able to do hands-on work and actually see the physical boundaries for where the spacecraft and the surrounding keep-out zones will be, and to be able to run through the procedure without a worry of actually damaging the real thing. It really helps to be able to practice ahead of time, and it streamlines things for the day of. In our last demonstration of it, we were able to cut down on the amount of time required to do the operation. There was some initial confusion on how to use some of the GSE or ground support equipment that's used to assemble the avionics into the rocket. After practicing, we were able to figure all that out, refine the procedure, and it made for a really speedy turnaround time. I've also been supporting some smaller mock-up activities. There are a couple that are a little lower profile, but are just as important. When the Orion spacecraft comes back to the processing center to be deserviced, it needs to be set onto a pallet, and that pallet has a certain way it needs to interface with the capsule. When it comes down, it needs to rest on 4 points. Each of those 4 points are kind of hard to see, and you don't really know where they are through the actual material of the capsule. So you can only set it down one way, and you need to know exactly where you're placing it and to know that it's on target. And to do this, we have a laser inclinometer, which is kind of a fancy machine that's able to determine the position of the capsule in 3D space. It uses a few mirrors and lasers to be able to triangulate exactly where the capsule is. And as of right now, that operation hasn't been performed, but we do have a mock-up capsule. So we're going to be using the mock-up capsule to perform that lift and setting it down onto the pallet. I came up with a bracket adapter assembly to be able to attach that inclinometer to the capsule, and from there we can actually perform the same operation without having to have the real spacecraft there. Again, it's all about streamlining the ability to practice those operations so that when the day comes and you actually have to do it with the real thing, it's a lot easier and you've seen it before. I've also been supporting a bunch of outreach activities where possible, and I always enjoy doing that because I love telling people about the program and getting them excited about what we're doing. For those who don't know me, I've always been a big fan of home projects. I love doing electronics projects, and I'm a big fan of model airplanes, so I always have some sort of project in hand that I'm working on. One of my biggest that I've been working on lately is my home rocketry program. I kind of run a miniature space program out of one of my rooms in my apartment, and that consumes a lot of my time that I would have spent driving to and from work. The extra time has let me do a lot of extra stuff on making new rockets and making improvements to some of the hardware that I have already. So you might wonder, how does one get started making their own miniature space program? And I happened to see a few YouTube videos online showing someone else doing something pretty similar. I saw a few videos of small scale rockets that were functioning just like the larger scale rockets, using guidance systems and all sorts of fancy electronics that I'd never seen before. And I thought that would be really interesting. So I reached out to him, we talked a little bit, and the more I talked to him, it seemed a lot more feasible. So after kind of getting a background of things that he ran into as failures and stuff to avoid, I ended up embarking on making my own first rocket. So the technology inside these rockets is really similar to the real scale, full-size orbital rockets that we see out at the Cape. These rockets don't have any large fins or passive stability features like a lot of model rockets you would see at the store or have built as a kid maybe. They all use a technique called thrust vector control, which is being able to angle the thrust off the main engine to be able to steer the rocket. I like to equate it to balancing a baseball bat on your hand. You're always trying to stay under the center of mass of the bat by just translating and moving the support that you have under the bat. That's basically what's happening inside the rocket. It is angling its engine to try and stay under the rocket as it tries to kind of go out of control. Nearly all modern rockets use thrust vector control. It's a great way to be able to control the vehicle while in flight. A rocket is inherently an unstable shape because it's just a tube. It has no wings or anything usually. So being able to just angle the engine and stay on course is a great way to keep things simple, light, and use everything that you already have on hand, which being simple and light is one of the biggest things that you want to maintain with these. Modern rockets like the SLS or Falcon 9 or any current launchers flying usually have multiple engines, and all of those engines can kind of move in concert together to steer the rocket. So I'm trying to work on that myself with having engines that are able to move together to be able to control the roll, the pitch, and the yaw of the vehicle. So those are each the different directions that you can turn in flight. And when you need to correct back another way, you need kind of a plan for how to do it. So that's a whole subject that could be its own individual video called GNC. GNC stands for Guidance, Navigation, and Control, and all modern launch systems use GNC software to be able to steer and operate in 3D space. To operate guidance, navigation, control, you need a few things. You need some sort of electronics that are going to fly on your rocket, which are called avionics, and you need some sort of control actuator system. So for me, I use a simple thrust vector control mount using 2 RC airplane servos. And that's basically all it takes to fly. My miniature rockets are also really similar to the full-scale ones because there is a delineation between flight software and ground software. On board the rocket, there is a thing called flight software. This is any software that runs on the vehicle part that flies. So there's a very different operation that goes on inside the rocket versus on the ground. So my launch complex has its own software, and they're both connected to each other via communication lines. This is really similar to the real thing. There's different umbilicals that connect to real rockets to actually electrically bind them to the ground system and be able to send signals back and forth to tell them how to do things to operate or even do software updates. For my purposes, I'm just able to do a software update over a USB cable, which really makes things simple, but originally I had wanted to do it through all the ground infrastructure, and that was a lot more overly complicated. There's a lot of testing that goes into this too, so the rocket and the ground system both have to be integrated and tested together. We do this for SLS as well in integrated testing. It ensures that everything end-to-end works and you're able to send a signal on one side, receive it, and get the necessary operation. I personally subscribe to the test like you fly method of software development. So I try and replicate what the rocket's going to see in flight as much as possible. As a result, I've come up with a test stand that I'm able to put the rocket on and be able to actually see its control system working. I can substitute a little propeller unit for a rocket engine and kind of tune the propeller to have a similar thrust to the rocket engine, and this lets me see how the rocket behaves under different responses. So when I push it, it's able to respond in real time, and I'm able to see how effective my control system is at working under a flight-like condition. It can be really hard to simulate a flight-like environment because it is so quick and it is so dynamic. So I've also come up with a few small simulations to be able to show how the vehicle is going to perform over time. I keep track of my mass budget so that I can be able to lift the entire rocket, and I have to try and make all sorts of decisions to lower the weight of all the components inside the rocket. One thing that I've kind of been refining since the beginning, which is really similar to big aerospace, is materials, processes, and procedures are always kind of improving. So I've been steadily refining some of my designs to be able to cut weight, make them more efficient, make them work better. And when things kind of dead end, I kind of turn back and try something new. I'm always trying to make the most of the different materials that I have on hand. I use a lot of the same ones that actual rockets use. So the engines in my rockets are sometimes actually an ammonium perchlorate and aluminum powder mixture, which is what the actual Space Shuttle and SLS booster uses. So chemically they're the same, but it's just a smaller package. I also use a black powder type engine where it has something more similar to a firework, and that makes a lot more smoke and fire, and it looks more impressive, but it isn't as high performance. The other thing too that my rockets share with the real ones is I use a lot of cork insulation on things. Cork is a wonderful material that is used on the actual boosters, and it helps protect them from the high heat of the flames coming out of them. So for my case, I have a bunch of 3D printed parts inside my rockets. And all of these 3D printed parts, when they're made, are printed using a high heat extruder. So they have to be melted to be built, basically. If the plastic is made to melt at a reasonably low temperature, it doesn't really work when it comes in contact with a flame. So, for my purposes, I've been coating my rocket motors and anything that I really don't want to melt in a cork insulation or a thermal ceramic paint. And these are very similar to what we use on the real thing. There's all sorts of cork around the boosters and any sensitive components that might experience that kind of heat. It's really light, it's really cheap, and it works great. The ground systems on my vehicle are kind of their own entire project. They've taken a lot of different improvements over time, and I'm really, really happy with where things are. So, much like a real launch system, I have a whole launch countdown procedure. So, as soon as you hit the launch switch, the rocket doesn't immediately launch. It actually runs through a countdown that takes about 20 seconds from beginning to end. So, at the start of the count, everything begins counting down. I even have a countdown clock to display the time until launch. Everything's fine until about 2 seconds. At the 2-second mark, there is a signal sent to the rocket saying, "It is now time to launch." This gives me plenty of time to be able to abort my countdown, and it gives me plenty of time to make sure that everything is okay right before it sends that signal. So at 2 seconds, it receives the signal that it's going to launch, and inside the rocket flight computer, it actually looks at its state and compares it with what I've deemed to be a launch commit criteria. So once it gets all the goes, it proceeds to send a signal back to the launch pad to say, "I am good to go and we are proceeding with the count." If it fails this check, it stops and the countdown is canceled. Once everything's given the green, then the rocket is on internal guidance and the guidance loop activates. At this point, it's waiting for the first movement of the rocket. It detects that using an onboard accelerometer, and the launch pad contains the ignition system to be able to light the motors. It's a little different than how real-world rockets actually ignite themselves, but it serves to keep some of the weight off the rocket. As soon as the engine lights, there's a really loud noise as it begins to come up to thrust. The plume inside the engine is basically an explosion that's continually going on, and as a result, it makes a lot of noise. So on board the pad is a sensor listening to detect an incredibly loud noise in close proximity. It's a little microphone I've basically tuned to cut out any outboard sounds or interferences like wind, shock loads, anything like that. It's just listening for the sound of the engine. And once it hears it, it sends that signal to the launch pad and says, "The engine is lit and we are proceeding." So That is the last check, and that is the last step, basically, that the launch pad has before it confirms that the rocket is about to go. From this point, it releases its launch clamps, and the strong back on the rear of the rocket lets go, and it falls away. At this point, the rocket is completely released from the ground. It's no longer held in place by the clamps, and it is free to take off. All of these kind of confirm that everything inside the rocket is working, the engine is lit, and the rocket is actually going to leave the ground. All of this didn't really happen at once either. I've been kind of building this up and adding safety features that kind of overlap each other and kind of protect things from going wrong under multiple redundant systems. So if the engine goes to light and it's a dud igniter, or if the engine sputters and it doesn't quite catch fully, it's not going to allow the rocket to be released, and that saves my vehicle and anything around it from a faulty launch. The pad uses a pretty similar design to the Rocket Lab Electron, the Antares, the Falcon 9, and it even shares some features with the SLS launcher. It has a clamp system that holds everything in place and allows me to do static fires, and because my launch pad can be lowered sideways, I can actually load my engines sideways, upright the rocket, and be ready to launch immediately. Being able to go sideways is a feature that I need personally to operate my launch vehicles, because I defer loading the rocket engines until I'm already at the field. They also have a vehicle stabilizer at the top that prevents the rocket from falling over due to any wind or anything else. The clamps are pretty strong, but this is just kind of an extra insurance policy on top of this. Getting to where I am on it now has been a very, very long journey of failures, improvements, learning from things, and kind of going in a complete circle of improving and making things better. I really operate completely on my own, so any mistake I have is my own, and I have to go back and fix it. So on occasion, I get things wrong, and I have to go back, look at the footage, look at the information I got from that launch, and then improve it for the next one. Each launch, though, improves the processes, the hardware, how I do everything around it, and has really, at this point, made a pretty great product that I've been putting together. So at this point, I have all these advanced systems that are able to halt the countdown, do go, no-go polls, and all sorts of extra things that I didn't initially start with, and I wouldn't have originally thought I needed until I encountered those failures along the way. Another thing that's been a big help too is being able to talk to people in the rocketry field. So I've met a lot of people along the way who have reached out to me, seeing the stuff that I post online, and asking questions about it, and the feedback has been really good. And on occasion, someone who knows a bit more than I do is able to lend a tip that actually helps me move along and maybe jump over a pothole that they had. It's also really helpful to be able to do that for other people, where in developing my own test stand to be able to test my software, I was able to give the idea to a few other people, and they actually were able to breed that into having an earlier success than I was. Over the duration of the project, I've actually learned a ton. It's only been about 1.5 years or so of doing a lot of this, and really only about 1 year of really doing it seriously. So I learned a ton about computer programming and mechanized electronics, being able to program machines that actually do things. I learned a ton about how to assemble electronics and actually be able to put things together. I learned all sorts of skills in circuit design and all sorts of things like that that I really had never really tried before. And on top of that, I got to be better at doing computer-aided design and modeling software, because I kind of had to push a few things of what I was able to do and try and come up with solutions that work with the 3D printing side of things and not necessarily what looks good or might sound good on paper. Because after all of these things have to live in reality, and because of that, they need to have a grounding in what is feasible. So I can design a part, but the question is, can I assemble that part or fit my hand inside of it? A lot of those influences have come from going to work and seeing how the different handling and access works, how the different operations are practiced, procedures for safety, different ways that the Air Force range operates. All of those have kind of influenced how I operate my own miniature space program, because those are things that work in real life and they translate. I have currently 3 main rockets that I've been working on. Depending on how you divide it up, that could be actually about 6, but in reality, it's about 3 rockets. So I have a Falcon 9 with 2 stages, so it has a core and an upper stage. I have a SLS rocket, which will have an upper stage eventually, and I have a New Glenn rocket with an upper stage. So all of those have their own challenges, they're all unique, and they all are kind of building blocks on each other. My first rocket that I put together was my SLS rocket. It kind of took on the form of SLS because the weight was something that was so much of an issue that I had to add extra engines to be able to lift everything. So in the end, I thought, why not take inspiration from what I do every day? And it turned out working out pretty well. The flight controller was a little simple. It was not coded by myself. It just used very, very simple control system from a drone, actually. From there, I decided I was going to get more serious into things, and I wanted to build my own flight controller and avionics for my rockets. And at that point, I was able to learn how to do circuit design, do a lot of prototyping on the side, and I actually started building my own flight controllers. So all the software inside the launch pad and inside the rocket that controls it and operates its different recovery systems and flight termination systems are all done by me. So I have had to learn how to do the code inside these things that makes them work, the different interfaces between sensors, how that collides with reality and clock time and data recording and all these different things that actually make it really hard to get a good success regularly. So reliability is a big problem right now that I'm solving. Last year I had my first success with my own software and my own flight controller design. From there I started actually making my own boards and having them sent out to a board manufacturer where they send me back a nice pristine printed circuit board. The printed circuit boards have been a huge help reliability-wise because it takes some of the risk off me being able to actually assemble these boards out of smaller components and wiring pieces individually. They get to come to me pre-made, ready to go. I just drop things in, solder it together, and then I have a completed set of avionics. To develop things, I've been using my Falcon 9 rocket. It only has 1 engine, it's a little lighter, and it's a bit more durable than my SLS. And because it uses less engines, I can fail a little more and figure things out to translate to the other rockets. It's had a total of 11 flights at this point, some of which more successful than others, but that's all been part of the process. As you change things, it changes everything about how it performs usually. The current version of the Falcon 9 that I have has deployable fins and legs that are able to open up on command from the flight controller. It has an onboard parachute that it ignites with black powder, so I've had to learn to make my own pyrotechnic devices and come up with procedures to safe and arm them without having any incidents. My end goal with my Falcon 9 rocket is to be able to fly it just like the real thing with an upper stage and a miniature Crew Dragon on top. It's hopefully eventually going to move towards propulsive landing, so I actually have made everything to have extra channels and extra functions to be able to point itself downward and get the engine in the right direction to be able to land on a second model rocket engine inside of it. So I know it's possible, and I've seen it done by a couple people online, and I've been talking with them a lot on how to make it work correctly, and their learning process from attempting to do it and some things that I've tried to integrate along the way. So that'll be eventually, but for now I'm just trying to get the core and the upper stage flying together, and that'll be really, really cool if I can get that by the end of the summer. All of the software that runs on the Falcon 9 that I'm making has been also copied over to work with my SLS. Everything uses the same avionics and a lot of the same parts. The SLS just has extra boosters, and those also have thrust vector control. So it's able to control itself in roll, pitch, and yaw, so it can steer completely in the air. It actually operates just like the real thing, where the core engine has a longer runtime than the boosters, and the boosters actually perform higher thrust than the core. So they're able to lift the whole stack together, and at booster burnout, they actually detach and fall away. My boosters actually have parachutes mounted inside them so that I'm able to recover them immediately after they detach. The core then continues onward using its engine and is able to achieve a higher altitude because it can maintain its trajectory using the thrust vector system inside of it. From there, the whole system parachutes back down and I can recover it and fly it again. In the future, my SLS is actually made to be in the Block 1B variant, where it has an EUS upper stage. So the whole exploration upper stage is almost a separate rocket, just like on the Falcon 9 with its upper stage. So each rocket has its own flight computer, its own engine gimbal, and its own engine. So I'm really excited to be able to get the SLS flying with the upper stage because it'll be over 5 feet tall and it'll be an incredible sight to see everything fall away from each other and stage. I also have a cargo variant that I'm working on with it, and even a mini lunar lander that I've been kind of fooling around with on the side for the future. And lastly, I also have a New Glenn that I'm working on from Blue Origin. This one's a little smaller. It's kind of the last one that I started working on, and it really has a lot of the add-ons that I've learned along the way that have helped me improve and make things a lot better. It's a lot lighter. I think it should have a lot higher end altitude, and it also can have roll, pitch, and yaw control using its movable fins. I'm really excited to be able to get this one going. It's pretty close to being ready to have electronics installed into it, but it's kind of on the back burner over the others. My big end goal is to be able to have multi-stage flights just like real rockets. So even though the rockets are only about 1/48th scale of the real thing, they perform just like the real thing. And with that comes higher altitudes and a lot better videography of onboard cameras and all sorts of other stuff I've been including as I go. It's been a really fun project. I've met a lot of people, and I have to say, after working on this and putting stuff out on social media so much, it's really great to be able to see some of the nice things people have to say and how much it inspires them to go do their own projects. I always try and work in a little bit of what I would do for outreach, giving a tour in the VAB or talking to a class, where I try and egg people on to be able to go and do their own projects and kind of see themselves that they're able to do it as well. And I've seen a lot of other people succeed and get started even down the road of making their own model rockets from just reaching out to me and sharing a few words. It's been a really big test of being able to actually kind of push through things and be able to learn on my own and find solutions for problems, which is something I really enjoy. And being able to see things as a collection of smaller things and attack each section at a time has been a really big learning opportunity as well. So looking at a project like this, it can be overwhelming to see that it has so many systems, it has so much refinement in it, how will you ever get to that point? But you have to start somewhere, and once you start, you kind of slowly roll towards that ending of having something that works really well every time and has a great level of refinement.